In the last video, we saw the four postulates of quantum mechanics. We also saw the measurement operator and its property along with an example. In this video, we'll learn a few more things about quantum measurements. So first of all, let's talk about projective measurement. It is a special case of postulate 3 where the measurement operators are projectors, and its definition says that a projective measurement or von Neumann measurement is described by the observable M, which is a Hermitian operator, on the state space with the spectral decomposition M equal to summation M P of M, where P of M is the projector onto the eigenspace of M and M is the eigenvalue of M. As said earlier, it is a special case of postulate 3 where measurement operators are projectors. That is, our measurement operator M will be equal to our projector P of M, where P of M satisfies the following condition of a projector operator. Also, apart from satisfying the completeness condition, that is summation M dagger M equal to I, it also satisfies the condition that all M's are orthogonal. The possible outcome of the measurement corresponding to the eigenvalue M of the observable M, such that upon measuring the state psi, the probability of getting M is given by P of M equal to rho of psi P of M ket psi, where P of M is a projector operator, and the state after the measurement, that is psi dash, will be equal to P of M psi root under probability of getting M in the outcome. The average value of measurement given by E of M for the observable M can be calculated using the projector operator P of M, such that E of M can be given as summation M times probability of getting M, which can be written as summation M times, and P of M is given by this expression, which is equal to rho of psi P of M ket psi. Now taking the summation inside, we will have rho of psi summation M P of M into ket psi, and this expression is equal to our observable M. So we can write E of M equal to rho of psi M ket psi, which can be also written as in this notation. Now, if you are not interested in the post-measurement state, we can use a mathematical tool known as POVM formalism, where POVM stands for positive operator valued measure. So by definition, a POVM is a set of positive operator EM such that summation M E of M is equal to I, and probability of outcome M is given by P of M equal to the average value of E of M, where E of M is equal to M dagger M, where M is our measurement operator. So for all POVM set EM, there exists a set of measurement operator M subscript M. That is, if we define M equal to root under E of M, where M is our measurement operator, which implies M is Hermitian. That means M dagger will also be equal to E of M, and from the measurement operator we have summation M dagger M equal to I, which implies summation M dagger and M will be equal to E of M, which is equal to I, as we stated here. So this was all about POVM measurements, which is the most general measurement in quantum mechanics. Now so far we have talked about measurement operators. Now let's talk about a property of quantum measurements of different quantum states, which says that non-orthogonal quantum states cannot be distinguished. Let me repeat it, that if we have a set of quantum states which are not orthogonal, then it is difficult for us to distinguish between them with certainty. Let's suppose we have a set of states from psi 1 to psi n, and out of these states, suppose Alice picks a state psi I amongst these states and gives it to Bob. So now Bob has to identify the value of I from the given set of states, and Bob can perform this task with certainty if the states given here are all orthonormal. which implies Bob can do a quantum measurement with measurement operator mi with outcome I to distinguish the states. That is, if suppose Alice chose the state psi 3 and packed it in a box and gave it to Bob. Now Bob doesn't know that the state is psi 3, and doing some quantum measurements he has to find out whether the state is psi 3, that is, the value of I is 3. Now he can do some quantum measurements to find this state only if all the given states are orthonormal. So we define a set of rules given by a function f of j, which is equal to I, where j is the measurement outcome, such that if Bob measures the state psi 1, then f of j will be equal to 1, since the value of I here is 1. Similarly, if Bob measures the state psi 3, f of j would be equal to 3. Now with all this information, we will try to prove that a set of quantum states are distinguishable only if they are orthogonal. So we will prove this by contradiction, that two non-orthogonal states psi 1 and psi 2 cannot be distinguished. So by contradiction, suppose a measurement is possible for our two non-orthogonal states psi 1 and psi 2, such that probability of measuring j, that is p of j, is equal to 1, for if f of j is 1 for psi 1 state and f of j is 2 for psi 2 state, where psi 1 and psi 2 both are non-orthogonal. Now we define EI, which is equal to summation j mj dagger mj, such that the average value of E1 with respect to psi 1 state is 1, and the average value of E2 with respect to psi 2 state is 1. And since from this definition summation I EI will be equal to I, it follows that summation I psi 1 EI times psi 1 will be equal to, since it is for two states, it would be psi 1 E1 psi 1 plus psi 1 E2 psi 1, and this would be 0. So obviously from this we say that this summation is equal to 1, and since psi 1 E2 psi 1 is 0, we can write root under E2 psi 1 is equal to 0. This is from the fact that EI is summation j mj dagger mj. So now suppose we decompose psi 2 in terms of two components, which is one that is parallel to psi 1, that is alpha psi 1 equivalent to psi 1, and one which is perpendicular to psi 1, that is beta psi 1 perp, where this state psi 1 perp is orthonormal to psi 1. So by normalizing this, we get alpha square plus beta square equal to 1, which implies beta is less than 1. And since psi 1 and psi 2 are not orthogonal, then root under E2 psi 2 will be equal to root under E2, and psi 2 is alpha psi 1 plus beta psi 1 perp, which would be equal to root under E2 alpha times psi 1 plus beta times root under E2 psi 1 perp. And since this would be 0, from here we'll have root under E2 psi 2 equal to beta times root under E2 psi 1 perp. So if you take the conjugate transpose of this equation, we'll have bra of psi 2 into root under E2 equal to bra of psi 1 perp root under E2 beta. And if we multiply both the equation, we'll have psi 2 times E2 psi 2 equal to beta square psi 1 perp E2 psi 1 perp. Now we can see that this value will be obviously lesser or equal to 1, and we also know that beta is lesser than 1, which implies this whole value would be lesser or equal to beta square, which is less than 1, which implies psi 2 E2 psi 2 will be less than 1, which contradicts this equation. Hence, our assumption that non orthogonal states are distinguishable is wrong. So, we proved with contradiction that orthogonal states are distinguishable. Another way to understand this condition is by defining a unitary operator u, which is equal to summation j cut of j into bra of psi j, such that u dagger u equal to u dagger is equal to I, which is a condition for our unitary operator, where the state psi j's are all orthonormal states. Now, if u operates on a state psi j, that is, u operating on psi j, will give us j. So, with the help of this unitary operator, we can easily distinguish the given states psi j's. So, we can say that if two states psi 1 and psi 2 are not orthogonal, then any measurement that tries to distinguish between them will have some overlap. Due to this overlap, any measurement will have an inherent error probability, making it impossible to reliably distinguish between the two states.